My name is Mike Waite. I'm the Director for New Plant Market Development for Westinghouse Electric Company. I hope most of you are familiar with Westinghouse, but I will give a little introduction here. The company was founded about 135 years ago by George Westinghouse, and it has always been in at the forefront of energy development. It was responsible for commercializing AC electricity, for instance, and it designed and built the first commercial pressurized water reactor in Pennsylvania in 1957. Since then, we've been constantly in the nuclear sector. Our developments have formed the basis of approximately half of the world's operating fleet. And today we focus 100% on the nuclear industry. We provide nuclear fuel, decommissioning services. We service existing plants, providing outage services and upgrades. And we also continue a significant focus on new plant technology development. That's what I'd like to talk about mainly today. And let me introduce to you the Westinghouse AP1000 nuclear power plant. I'd like to frame this in the context of how nuclear technology has developed since those first prototype reactors in the 50s. Those we call Generation 1 reactors. There's a number of different types of reactors, pressurized water reactors, boiling water reactors. They were developed over the 60s and 70s to what we see today as the main Generation 2 fleet. You also see there are examples of pressurized water reactors and other technologies. There are a few Generation 2 plants still being built. There's some Chinese and Russian technologies being completed, some historic projects only now being completed. But the majority of new builds today are Generation 3 and Generation 3 plus plants. The Generation 3 plants were an evolution of the Generation 2, more safety systems, typically larger plants, and certainly increased operational and safety performance. But there's a significant step change between Generation 3 and Generation 3 plus. This was the result of a request from utilities and also from regulators to enhance the safety systems, provide more safety, but do so with a fundamentally different system using passive safety systems. Also, operations were improved. There was a call to improve manufacturability, deployability using advanced systems. But let me come back to those passive safety systems. What does that mean? What it means is that the ultimate safety systems use only natural forces like gravity, conduction, and convection, to power those natural safety systems. A feature of them also is that even with no AC power, no operator action, they will stay safe, cool the reactor in the event of unlikely event of an accident for at least 72 hours. This is what we call the coping period in the event of station blackout. So let's just talk a little about that station blackout. That is basically what happened at Fukushima. If we remember back to that incident, which really reset the nuclear industry for some time. The reactors actually shut down perfectly after the earthquake. All the safety systems kicked into gear, but when the tsunami hit, the diesel generators which were supporting all those safety systems, all the pumps, all the motors, etc. When the tsunami hit, those diesel generators became inoperable, and the reactors were then allowed to overheat. For a passive reactor using old passive safety systems, all of those safety systems remain fully operational during that station blackout. Put in simple terms, instead of a pump driven by a motor supported by a diesel generator, you basically have a tank of water which is located above the piece of equipment you want to cool, so that gravity can be used to provide that cooling water. So as well as increased levels of safety, you can also build in a great simplification of the nuclear power plant. This can have significant advantages during construction, during operation, less equipment to maintain, and also at end of life, there's less equipment to decommission as well. These plants are also built emphasizing modular construction techniques and advanced construction materials. This can really have a tremendous advantage in terms of allowing parallel paths. They reduce the risk of a challenge in one area of the construction site affecting the whole construction schedule. It takes operations off-site, leads to a less congested construction site, and also emphasizes factory build. This increases quality, productivity, and again can really lower the risk of the critical path items on that construction schedule. One more factor of the AP1000 plant, typical of many Gen 3 Plus plants, is its advanced load following capability. Now, we always think of nuclear power plants as perfect baseload generators, and of course you want to utilize that economic carbon-free generation for as much of the time as possible, but they are actually equipped to load follow. They can do this very efficiently and effectively. With the AP1000 plant, this load follow is achieved by mechanical means, and what this implies is that there is no chemical changes required to load follow, which is typical of many plants, and this has significant environmental advantages because you're not changing water chemistry. So the AP1000 plant is able to deliver clean, safe, and reliable baseload power, all load follow, and it is also a fully proven plant. There are 4 units in operation, which I'll tell you about in a moment, and it's been licensed in several countries around the world. So I mentioned those Generation 3 Plus plants are the latest available nuclear power plants. The AP1000 plant shares some of its characteristics actually with some of the SMRs being developed currently. Most of the small modular reactors are also Generation 3 Plus passive plants, taking a lead from the AP1000 large nuclear power plant. And I'd like to just compare and contrast some of those attributes. So again, both offering those advanced passive safety systems, which allow the technologies to simplify and also offer standardization of the plant. Just one illustration of that fact. The AP1000 plant has approximately a quarter of the volume of concrete to equivalent Gen 3 large nuclear power plants. So there's a tremendously reduced footprint, seismic building volume, less equipment, etc. Which when construction experience is incorporated, can really influence a shorter and more reliable construction schedule. So I mentioned also the modular construction, obviously a feature of small modular reactors as well, and the load follow capabilities, that 72-hour coping period. Now, small modular reactors, as you would expect, have a lower cost per reactor unit because they're smaller, but we are seeing significantly lower costs of electricity in terms of megawatt hours from the large generation 3+ nuclear power plants. There's some significant economies of scale that can be enjoyed there. And if you're thinking about deploying a nuclear power plant, obviously the licensing process, the environmental impact assessments, the site assessments, all those have to be done for a large plant just the same as they would be for an SMR. So again, you're consolidating those costs into a much larger producer of electricity, which is significant. The big difference here that you can see is though that the AP1000 plant is clearly has a global licensing pedigree. It's been licensed in the US, in Europe, in China. There are multiple operating units, and the challenges which all first of a kind technologies will see have been overcome now in the AP1000 plant, and those lessons learned incorporated into the design, the delivery model, and it really stands ready to be deployed efficiently and effectively on a global basis. Okay, so let's have a look at some of these AP1000 units currently in operation. So we have 4 AP1000 units in China at the Sanmen and Haiyang site. They were commissioned in 2018 and 2019, and that commissioning performance was really historically successful for first of a kind units. The testing program was expected to last about 10 months. Actually, the program was completed in 5 months because of the success of the tests. All tests passed first time, no unplanned trips or events during that testing period. The unique features of the AP1000 plant were all tested, the passive safety features all operating superbly. The operational parameters of the plant were also checked, so the load follow capability was tested, and really displayed itself as a plant which was easy to operate. The man-machine interfaces absolutely superb. Also, this proves that the plant is first of all capable of being built. It's constructible. The passive safety systems all proven. The testing program itself proven as being absolutely robust, and the operational parameters are actually above design values. So really tremendous performance. You see there a picture of the Sanmen plant with Unit 1 in the foreground, Unit 2 in the background. Sanmen 1, as I said, the first unit to be commissioned and the first to go through its first cycle. Really tremendous event-free, trip-free first cycle performance, as you see in that indicative graphic below. You also see there a brief outage for a Chinese national holiday at the grid operator's request. The operational systems took the plant quickly and efficiently down to standby, and automatically when the grid operator requested, back up to full power again quickly and effectively with minimal operator inputs required. So really tremendous performance. The owners of the plant and the Haiyang plant are absolutely delighted with the technology, the safety systems, the operations, and the performance. Okay, so these are the 4 operational units in China. We also have 2 units in an advanced stage of construction and commissioning at the Vogel plant in Georgia in the US. Some recent key milestones at the Vogel site. So Unit 3 is our most advanced AP1000 unit at the Vogel site. The Vogel site is an existing operational plant. There are 2 Westinghouse units, older Westinghouse units at the plant, so they're units 1 and 2. The new AP1000 units are units 3 and 4. Unit 3 at the end of 2020 completed its cold hydro testing. This proves all of the pipework in the nuclear island. And also, you see in the graphic there in the picture, Unit 4 having its shield building roof placed on top of the shield building also at the end of 2020. The upcoming milestones for these 2 units, well, Unit 3 will soon be completing its hot functional testing. This is a absolutely key milestone prior to fuel load. And Unit 4 will have its last major module placement. This is the passive containment cooling water storage tank that gets placed on top of the shield building and gives the AP1000 plant its distinctive profile. The Vogel site has of course had its challenges with the COVID virus, like every industry and construction site around the world, but still achieving significant milestones, still working towards a fuel load this year, and that regulatory approved commercial operation date in November of this year. It'll be great to see those come online, and the Vogel units have benefited from lessons learned from the China plants. There's been some ease of construction improvements made on the Vogel units. Also further ease of construction improvements have been made to the design and incorporated into the standard design, such that future builds will equally benefit from from all those lessons learned moving forwards. So with that, I would like to commend South Africa, Kenya, Ghana, all those countries in Africa which are considering new build to embark on this, what is basically a 100-year initiative with the latest Generation 3+ technology, but to do so with a proven technology, one which has proven it can be built, deployed, operated successfully, which is the AP1000 plant. Thank you for your time, and I hope you enjoyed this presentation. Thank you.